So yeah, model evaluation metrics. One of the reasons that I really like to cover this in some depth is that this is like a way bigger part of your job as a data scientist or data analyst, or even, excuse me, as a machine learning engineer, than most people think. So most people sort of have the sense that like life is a casual competition when you're a data scientist. You're going to be given a data set, you're going to be given a problem statement and like a loss function optimize, and then you have at it and hopefully you do a great job. But that actually kind of, I would say, vastly understates the scope of the problem. Probably, apart from collecting the data and cleaning the data, which obviously is a big chunk of work too, picking the right model evaluation metric to figure out how to even assess the performance of your model is like a really big task. It's something you want to be thinking about a lot. It's not the case that the world has these things figured out, even though like most people tend to assume so, right? Like we tend to think that when we're going to go walk into a new company or something, surely someone must have figured out what metric we should be using. Surely somebody knows. Surely there's an adult in the room. The answer is there's generally not. There really isn't an adult in the room. People haven't figured this out. And even if they think they have, you're always better off acting as if they haven't. Always better off thinking from first principles, from scratch, trying to think of, is this the right metric? Should we be using something else? Or like, why this metric? Those are all really good questions to ask because very often you will, in the process, spot things that other people haven't spotted. And that's a great way to drive disproportionate value. So there are a couple metrics that people generally understand like less well, and those are the ones I want to focus on today. One in particular, which is entropy. Entropy is somewhat, or can be somewhat challenging to develop an intuition for. So I want to provide you with like my best attempt to kind of convey the intuition behind entropy here. And I'm going to kick things off though with a quick discussion of some regression metrics first. So that being said, we're looking at two regression metrics here on this page. The mean absolute error, the MAE, and the root mean squared error, the RMSE. And both of these have sort of fairly intuitive interpretations, and they have pluses and minuses. I want to look at each expression in turn, just to kind of warm us up a little bit, get us looking at equations, thinking about them, and thinking about how to map the math onto the physics, onto the real world, onto life, onto business problems. So let's take a look at this MAE just to start. I'm going to zoom in a little bit here. So what we have is an expression that seems to add up. So that's what the sum term is doing here. It's the sum from J. You can think of that as a sample in the test set or in the training set or whatever data set you want to evaluate the performance on. So J is from sample 1 to sample n. So where there are n data points in let's say the test set. So you're running over n data points from data point number 1 to data point number n. And you're going to add together these terms here. So what are these terms? Well, yj, y sub j, is the predicted value that your regression model puts out. So let's say you're trying to predict the salary of a person based on like their resume or something like that. So what you would do is you would feed in the resume into your black box algorithm. It would spit out a salary, and that would be actually the prediction of the model is y hat j. The true value is yj. So usually the hat is meant to denote like the output of a model. And sometimes in statistics this is referred to as an estimator. Y hat is the estimator for the variable yj. Okay. So what is yj, the true value, minus y hat, the predicted value? Well, that's how wrong you were, right? If yj minus y hat is a really, really big number, then that means there was a big difference between the predicted value and the real value, and therefore your model did really poorly on that particular sample. The problem, of course, is sometimes your model will overestimate the value of the thing it's trying to predict, and sometimes it'll underestimate it. If it underestimates it, y hat j is going to be negative. So, sorry, not negative, rather. Let's say, okay. Let's say a person's salary is like, I don't know. Let's say a person is actually unemployed. Okay, yj is 0, and let's say our model wrongly predicts that the person's salary should be like $20,000, right? So in that case, yj minus y hat j is 0 minus $20,000. That's a negative number, and that's not great. We don't want those negative numbers to cancel out other positive numbers in the sum, and that's what these bars are for. They're basically telling you you're going to take the absolute value of whatever inside. So, if yj minus y hat j is negative $20,000, then this would just say, okay, forget the negative sign. We're just going to make it positive, and that way we'll add up the positive contributions of all the errors in the sum for all the samples in that test set. Okay. So once you've done that, you've added all the errors. That's like how wrong your model was across all your samples. You divide by the number of samples, and that gives you the mean average, or sorry, the mean absolute error. Okay, so that's where the name comes from. It's the absolute, like it is literally if you close your eyes and grab a sample in the test set, and then you say, on average, how wrong would I expect to be? That's the mean absolute error. Okay, so that's actually very, very intuitively interpretable. It's pretty clear what that refers to, and for that reason, that's definitely an upside. Is a highly interpretable metric. Okay, let's just take a quick gander at our MSE. So you'll notice very, very similar, almost identical expression underneath the square roots. Ignore the square root for a minute. What do we have inside? We have that 1 over n again, so we're averaging over our samples, let's say in the test set. Sorry about this. We also have a sum from the first sample all the way to the nth sample in that test set. And now, instead of just doing, so this is the main difference here, yj minus yj hat, instead of just doing, as we did up here, like these bars for the absolute value, instead we're going to square it. So what does squaring do? If you think about how this would affect, in practice, a prediction, right? So let's say we have somebody who we say is going to make, I don't know, they're going to make $1 this year. That's our prediction, right? YJ hat. And then in reality, they make $2, right? So then you get 2 minus 1, which is 1, and you square it, you get 1. Okay, so if you're off by 1, you take a hit of 1. That's like the contribution of that term in the whole sum. But what if that error doubles? So like what if instead of guessing a salary of 2, we guess salary of 3? Right? So now we guess salary of 3, that goes here. The true salary was 1, so then the difference is 2. When you square 2, you get 4. So if you're off by just 1 unit, you get an error of 1. But if you're off by 2 units, you get an error of 4 in the sum. So what this is effectively doing is it's saying, hey, it's actually even worse to be, it's more than twice as bad to be wrong by a factor of 2. Right? So this is actually somewhat common. You can imagine, let's imagine a concrete example like in medicine. If you're a doctor or pharmacist prescribing some drug and you get the dose wrong by I don't know, 10%, right? That's like most of it, like, okay, that's not great, but it's okay. Versus if you get the dose wrong by 20%, getting it wrong by that extra by 20% is more than twice as bad than getting it wrong by 10%, because there's like a sense in which you can overdose, and your risk of overdosing goes up very quickly as you start moving away from that optimum. So a mean absolute error would really not be the best thing if you're talking about a high stakes like pharmaceutical type application, where again being wrong by 2x is more than 2x is bad. Whereas the RMSE will naturally capture that. So it sort of disproportionately weights bigger errors. So if you have a couple of really significant errors in your data set that you really want to avoid, then your RMSE is going to force them down if you use that as your metric. That's going to flag those issues, which again is appropriate in some cases, less appropriate in others. One of the challenges that this introduces, though, with this squared term mathematically is before we said, okay, we're going to imagine a situation where we're estimating let's say we're estimating the amount of drug that you need, like the number of grams, let's say, of Advil or something that you should be prescribed. What this does is it squares that number. So you get some number of grams squared here. Now grams squared isn't really interpretable. It doesn't really mean anything. And that's why the square root comes in at the end. So we take the average 1 over n here, of the squared errors, and then we have to take the square root to make sure that the units still make sense. Because if we didn't have the square root, then the stuff in here would be you basically be giving somebody an error that's measured in like grams squared, whereas the prediction is in grams. So you can't really say like, oh, I say you should issue the patient like 1 gram plus or minus like 2 grams squared or something. That doesn't make any sense. You need to apply that square root to make sure that that the dimensionality works out. So any questions about the sort of the basic math behind that? Just get us warmed up a little bit here.
Yeah, I have a more general question about like what's the necessity of using or understanding like mathematical notation like every day? I mean, like that's fine and all, but is that really necessary?
Yeah, so this is a really good question. I'll say in general, some notation, like yes. You don't have to know product notation. You don't have to worry about like integrals, especially if you're not a like machine learning engineer aiming to be that. If you're like data scientist, data analyst, understanding the sum notation is helpful for actually exactly the reason that we're exploring right now. It allows you to speak kind of more explicitly about the structure of different loss functions and things like that. But you don't have to take it very far. Like I think literally the most important thing is the sum notation. If you get like sum from j equals 1 to n, like if you understand what that means and like that the subscripts j here indicate like a specific sample and y sub j is the y value for a specific sample j, if you get that, then like pretty much you're good to go. I wouldn't say, especially for analytics or like business focused data science, you don't need to, yeah, you don't need a black belt in like mathematical notation, but knowing the summation stuff, the basics of it is important, I would say. Does that make sense?
Yeah, sure. Thanks.
No problem. Any questions? Any other questions or questions about this stuff? Yeah, Isaiah, go ahead.
Um, you went over, I guess, one case for why you would use one of these measurements over the other. Could you explain more of why you use mean absolute error versus root mean square error?
Yep.
Or
Oh, sorry.
or just pros and cons of each, or another case?
Cool. So I'll take that as an invitation to just show the next slides because that's exactly what I'm going to get into. So um, pro for the MAE. The big pro here is interpretability. The MAE is so stupid simple, right? Like it is the average wrongness of your model across your samples. That's it, right? Close your eyes and reach in, grab a sample in the test set. How wrong do you expect it to be on average? That's the MAE. So right away, for business people trying to understand analytics, trying to understand data science, like your job as a data scientist or a data analyst becomes way easier when you deal with that metric. So interpretability is nice. The downside is it often doesn't reflect the dynamics. So it is true that more often than not you will find the RMSE used simply because usually it's the case that being wrong by more than 2x, being wrong by 2x is more than 2x is bad, right? Usually it's the case that like we really care about getting a prediction really accurate, close, like we want to get really close, and the more wrong we are, like we're embarrassed by our prediction, by our wrongness, it like out of proportion to the actual scale of the wrongness itself. If you make, I don't know, if you're doing house price predictions and like you have a home that goes for $500,000 and like your model predicted that it should go for like 450K, then you're going to be like, that's pretty bad, but it's okay. Whereas if it predicted that the house is going to go for 400K, then like yeah, you feel like you're like, oh, that's really embarrassing. It's more than twice as bad, at least I would say. You can hear even in the tone of my voice that like this is pretty arbitrary, and it definitely does have to reflect the specific business context that you're applying it to. So this is sometimes a gut thing, but often it speaks to business problems. It speaks to wondering like how does this company make money, and which metric is most closely and directly tied to how this company makes money. And that's usually the question, or like to the specific problem that you're trying to solve. Usually our MSE is that. Users tend to like dislike recommendations more than twice as much if they're twice as bad. So it's pretty common for RMSE to be like the go-to. But again, if you if you're going to try to defend something, if the RMSE and MAE tell a similar story, or you really favor like interpretability for some reason, like you're talking to people who are not stats savvy, or your problem happens to have very linear dynamics, and all you care about is like, if it's twice as bad, then it's, if you're off by twice as much, twice as bad, then MAE is your go-to. That's really at the core of this. I think one of the biggest challenges is people get lost in these metrics and think that there's like more analyzing to be done. It's worth reading into them a little bit, and there is a little bit more to say than what we've covered here, but frankly, for the vast majority of practical purposes, this is all you'll need to know. Anyway, yeah, so I guess hopefully that answers your question, Isaiah.
Yeah, thanks.
Yeah, no problem. And Hadrian? I thought I saw you unmute, but
I was going to ask a similar. I was going to ask, like, why not just use the RMC as opposed to the MAE? Like, why have both and just not stick just to RMC? But I think you kind of answered my question, because the MAE is simply simpler and it's pretty good to use to analyze like linear dynamics, like you said. So yeah, I'm good.
Perfect. Okay, great. And yeah, I mean, keep in mind there are occasionally problems where the MAE will make more sense and your mileage may vary, but in general, this is it. And if you go on Kaggle, you'll also notice it's quite rare to see an MAE loss function for a Kaggle competition. Most often, it's going to be RMSE if it's going to be one of those two, and that's more or less the reason why. Okay, really quickly touching on precision versus recall, just to try to build a little bit of intuition around this. I want to focus on precision first. So I'll use COVID as an example. It's a little bit, it's maybe too soon, but I think it's pertinent. So precision is a metric. Let's take a look actually at the math first. So true positives, these are the number of samples that are, let's say for COVID, that are actually positive. So the number of people who actually have COVID, who you correctly say have COVID. On the bottom, total predicted positive, this is like the number of times you have guessed COVID, the number of times that your algorithm overall, over let's say the test set, has guessed that a given person has COVID. So one way that you could game this, right, if you wanted to like to set up, one way that you could game a test that was just accuracy based, like that you could make your algorithm look really good if you're just using accuracy as a metric, is you might say something like, got my thoughts garbled. Let me just rewind on that. I apologize. Okay, one risk when you're setting up a test like a COVID test is that you will either wrongly say that somebody doesn't have COVID when they do, or you will wrongly say that somebody does have COVID when they don't, right? Those are the two kinds of mistakes. The precision is you can game those two types of mistakes if those are what you care about. If you wanted to make absolutely sure that you caught every single COVID case, you could just guess that everybody has COVID, right? That'd be one way to cheat the system. And in that case, essentially you'd be guessing like your total predicted positive would be huge. You'd be guessing that everybody and their grandmother has COVID, but the actual number of people who has COVID is probably going to be pretty small. And so your true positive over your total predicted positive is going to be a really small number. Your precision, in other words, is going to be really low. So what precision tells you is like, if your precision is high, that means that you're not just throwing this label around, the positive label. You're not just guessing that everybody has COVID in order to be able to say that like you haven't missed anyone. That's what this is checking for. Some algorithms are really kind of cautious, and they try to guess that everybody has the disease or everybody's in whatever class it's interested in categorizing. And that can be a problem. It can be something that you don't want. And the precision is what tells you whether or not that's a problem. If you actually are just throwing around this label, you're saying you're throwing the COVID label at everybody who gets tested just because you're terrified of like telling somebody that they don't have COVID when in fact they do, then your precision will be really low. Your true positive, the actual people who have COVID when you say they do, is going to be way, way smaller than the total predicted positive, because total predicted positive will be huge. You're just throwing that label around. So for precision, this is kind of the catchphrase that I like to keep in mind. It's like, I'm not just throwing that label around. Precision is you trying to prove that. It's trying to prove that your model's trying to be discerning in its assessment of who has whatever target label and who doesn't. Does anybody have any questions on that? Okay.
Just real quick, you wouldn't apply any of those metrics, so accuracy, not accuracy, recall and precision to a regression problem. This is only applicable for classification problems, right?
Great question. Yeah, you're exactly right. Yeah, that's right. I should have mentioned that. So at the top I just wrote, classification metrics, precision versus recall. You're totally right. If ever anybody starts to talk about precision and recall and it seems like they're talking about a regression problem, you have the right to scratch your chin and go like, wait, that doesn't make sense. These metrics, you're right, are only defined for classification problems. Yeah. Great. Okay, that brings us to recall. So recall is, in a way, it's sort of similar to precision, or it's almost like the mirror image of precision. So what we get here is essentially proof. If your recall is really high, you're proving that you're not doing exactly the opposite. You're like basically trying to avoid assigning that COVID label to people. Because if you look at the expression, you've got the true positives. So again, same thing that's on the top for the precision. So this is the people who actually have COVID when you say they do, divided by the total actual positive. So essentially, if this number is really low, that means that you're not actually, you're not recalling everybody in the data set who actually has COVID. You're basically missing some of them, right? So a way to one way that your recall could be really bad is if you basically ignore the COVID label, is if you basically avoid saying that anybody has it, in which case your true positive goes to 0, right? Because you're not assigning the COVID label to anybody, but your total actual positive is going to be some number, whatever the number of people who truly have COVID is. So these are kind of two sides of the same coin, precision and recall. They balance each other out. If you're throwing the target label around that you're trying to predict, if you're basically saying that everybody has COVID, or everybody has cancer or whatever it is, then your precision will be really if you're just throwing it around, your precision is going to be really low, right? You're not being precise with it, and your recall is going to be really high. It's going to be actually 1. And on the flip side, if you're going, okay, I'm going to be super cautious with this label. I'm not going to assign it to anyone unless I'm like way ridiculously sure that they do have COVID or they do have whatever, then the reverse will happen. Recall will be 1 and precision will be 0 or very, very low. So that's just, I guess, one way to think about these two things. Hopefully these two lines are helpful, at least memory aids, to think about the spirit of what these things are getting at. And any questions about recall or precision? Cool. Okay, now on to the meat of the show, entropy. Okay. Entropy it's a classification metric as well. So to Hadrian's point, if you ever see anybody talk about entropy in the context of regression, that's nonsense. It doesn't work for regression. It is a measure of how well sorted a group of points is. So what I mean by that is you can imagine like a group of points, each of which belong to different classes. So maybe a third of them belong to class 1, a third belong to class 2, and a third belong to class 3, or something like that. Entropy is a measure of how mixed up, how jumbled that set of samples is. If that set of samples has only class 1, if it's pure class 1, then the entropy will be really, really low. If it's pure class 2, the entropy will be really, really low. Actually, it'll be 0 in both cases. And if it's pure class 3, it'll be 0. But if it's a mix, if it's got some class 2 and some class 3 and some class 1 or whatever, then the entropy is not going to be 0 and it's going to be some number. And the more of a shit show it is, the more of a mix it is, the higher the entropy is. Entropy is a really deep concept that comes ultimately is maybe too strong a word, but originally came from physics. It's since been used in computer science, and there are a lot of actually deep parallels between the usage of entropy in computer science, the usage of entropy in physics. They're actually the same thing. But anyway, it's a fascinating topic, but for data science purposes, the bottom line is entropy tells you how messy a data set is, how jumbled, how much of a mix of different classes you have in it, and a more pure set of data points, in other words, a set of data points that all or almost all are the same class, is going to have very low entropy. So this is an interesting measure because it allows you to tell, like, how did your model perform? Because classification models, essentially, their whole job is to sort samples into different buckets that are pure, right? Like if your model is working perfectly, if you have a COVID model, and it's designed to predict, do you have COVID or do you not have COVID, then its job is basically to take a data set, which is this jumbled mix of some people have COVID, some people don't, with high entropy, and then take that data set with high entropy that's a jumbled mix. Your model is designed to turn that data set into two piles. One that it says have COVID, that just contains people who have COVID, so in other words, that's low entropy and pure, and the other, same thing, but for people who don't have COVID. So basically, a machine learning model is something that's designed to bring order to the world. It's something that's very literally designed to reduce the entropy of your data set by sorting into two different data sets or more if you have more classes. But that's the fundamental philosophy here is we're trying to go from this disordered mess and jumble of stuff into neat piles that we can associate with classes. So that's why entropy is a really interesting metric. It literally tells you, did my algorithm do well? Otherwise, you can imagine it would be really hard to find a way to kind of measure how well different classes are separated, especially when you're looking in at a sort of a multi-class problem. So that's what entropy is going to get at. Actually, before I dive into it, does anybody have any questions with that sort of basic introduction to entropy? Okay. Cool. So my goal here today is starting with that framing. I want to really give you a concrete walkthrough of how entropy works with a toy example. And I'm not going to show you any equations until the very, very last part of this. And then the only equation I'm going to show you hopefully is going to make sense right off the bat because it's going to use the illustrations that will build up on the way to kind of just make things concrete in math terms, but you'll get the math without looking at equations first. Okay, here's the fundamental question that entropy is going to try to answer for us. If we were to take a data set that looks like this, and here I've got, so a point is a sample, and each sample is colored, so they belong to different classes based on color. We've got a blue class, we've got a red class, we've got an orange, yellowish class, and we've got a green class. Now, suppose that we're allowed to ask yes or no questions and sort these samples based on whether they answer the question with a yes or a no into different buckets. How many questions will it take to sort this data set into perfect buckets that are totally pure with only one color in each? Okay. So hopefully it'll become clear as I actually show how this works. So the first question, for example, we might ask is the sample red or blue? One of those two. Is it one of red or blue? If the answer is true, then we're going to put it in this pile. If the answer is false, we'll put it in this pile. And next, we have to ask another set of questions to split these up further into the final kind of neat buckets at the very end here, right? So first we say, is it one of red or blue? And if the answer is true, you put it in this bucket. If the answer is false, put it in that bucket, fine. And then one more question, is it green here? Allows you to split off into a green pile and an orange pile. And is it blue? Allows you to split it off into red and blue. And now we have perfectly ordered piles. So it took us two layers of questions in order to go from this jumbled mess to a set of four pure piles. Now, if you think about this for a second, this is actually a kind of a nice, I think I have a nice little, there we go, nice little boxes. All right, this is kind of a nice, there we go, there's the number 2. Okay, that's the number of questions it took. This is kind of a nice way of quantifying how messy the original data set was. Because the more questions you have to ask in order to finally clean your room, so to speak. I mean, if you imagine these are like textbooks or something, you're going to put them in neat piles in your room. The more questions you have to ask, like the more messy the original data set must have been, right? That's sort of the intuition. These questions are kind of like us putting in work here. We're actually going to like have to go, okay, like let's put the red and blue books over here. Let's put the orange and green books over here. So, maybe history and literature goes over here and science and tech goes over here. And then you have to, ask a follow-on question to subsort from there. So this is starting to give you a bit of a sense of like the philosophy that Entropy is going to use to answer this question of like, how messy is this original data set? Well, it's as messy as the work that we're going to have to put in to sort it. That's the intuition. And anyway, in this example, we see we have like 2, right? So essentially that's the cost of cleaning things up. So that number 2 is actually going to tell us something quite meaningful, right? About the amount of disorder that there was originally in that data set. Okay. One interesting, or actually, sorry, a more correct way to express what entropy is asking is it's saying if you were to close your eyes and you didn't know what color any of these points were, close your eyes, reach in, pick out one of those samples. On average, how many questions would you expect it to take before that sample was sorted? Okay, so in this case, it's actually 2 because every sample ends up taking the same, you have to ask the same number of questions for every sample type. But there are cases, as we'll see, where things get a little bit more complicated. But basically, this is the idea. So entropy is, if that last little bit didn't make any sense, totally fine. Bottom line is, entropy is the number of questions that it takes to kind of clean up this mess. And any questions about that so far? That intuition? Okay. Hopefully that's because it's clear. But just to check in, Geethika, is that clear? Oh, you're muted right now, and I'm not sure if you're... also, you might be unable to talk. Okay, awesome. Thank you. Cool. So that's the philosophy behind entropy. Let's look at a couple of examples. We're going to try to now piece together the actual formula for entropy using examples. Okay, here's a problem with one class of sample. So you imagine like a pile of books in your room, and they are all history books. You've now got a pretty clean room. The entropy is actually 0. But let's look at some of the numbers we might associate with this pile of books. So we have one class. The probability of a sample in this data set belonging to each class is 1. Like if you grab a book here, there's a 100% chance that that book is going to be a blue book, right? There's just, 100%. And the number of questions that it takes to sort this pile of books is 0, right? It's already sorted, so you're done. Okay, but what if we have something like this, right? We have a 2-class problem, a pile of books, and 4 of them are red, 4 of them are blue. Well, now the probability of a book belonging to each class is 1/2, right? If you close your eyes and pick a book, the odds that, for example, it's red is 1/2, right? The number of questions you have to ask to sort it is 1. Okay, let's see if we can spot a pattern. 4 classes. In this case, the probability, if you close your eyes and reach into this pile of books, the probability that you're going to grab, let's say, a red book or a blue book is 1/4, right? Each class has a probability of 1/4. As we saw a moment ago, the number of questions you have to ask in order to sort this pile of books into pure piles is 2. And we'll do one more just for kicks. If we had 8 classes, the probability of each class is 1/8, right? Close your eyes, reach into that pile of books, and the probability that you get like a green one, say, or a black one is 1/8. And it takes 3 questions to sort through that whole pile. Okay. Let's see if we can take these numbers and spot a pattern. I mean, I'll flag the pattern before we start. So first thing you'll notice is like the number of classes is just like 1 over the probability of each class. That's pretty obvious, right? 4 classes, 1/4, 8 classes, 1/8. But what's really interesting is look at the relationship between the number of questions and the number of classes. So 0 questions, 1 class, 1 question, 2 classes, 2 questions, 4 classes, 3 questions, 8 classes. It kind of looks like 2 to the power of the number of questions will give you the number of classes. Right? If you think about that, 2 to the power of 0 is 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. And that's actually not a coincidence because you have essentially like an exponential, these trees of questions are growing exponentially. And they're growing exponentially at a power of 2 because there are 2 possible branch points at each level. Here's how that looks in math. So we just said the number of classes is 2 to the power of the number of questions. Okay, let me just zoom in a little bit here. But the number of classes itself is 1 over the probability of each class. And so what we want to do is relate the number of questions that it's going to take to sort a given sample. We want to relate that to the probability that a sample will belong to that class. And anyway, that ends up being log base 2 of 1 over p. That's like, this is the only bit of math trickery that you actually need to understand in order for this to all make sense. Does anybody have questions about this? I'm happy to re-explain this in as many different ways as is necessary. Sorry, yeah, Hadrian was saying I had to head out. Anybody have any questions about this, this math part?
So how does this change the more unbalanced our data set is?
Yeah, okay, awesome. You keep asking like questions that portend the very next slide. I will answer that question in like a second. It's an excellent question and a good call out. Are there any other questions before I move on to that one? Mohammed, is everything cool? Cool. All right, I'll do one last check just for completeness here. Austin, everything cool?
Yep, all good.
All right. Okay, so yes, to answer Isaiah's excellent question here, what if the probabilities are different? What if things are imbalanced? Because so far, I mean, you're entitled to be like, okay, Jeremie, like cute story, but you've picked some really conspiratorial examples. Like, really, all the samples belong to the same class, exactly half and half, exactly a quarter, exactly an eighth. Like, you're picking some really hand-picked examples. What about something more realistic? What about something like this? Okay, so in this situation, we have half the samples are red, and then a quarter are blue, and a quarter are green. So what happens now? Like, how can we generalize what we've just done to this? Okay, well, we want to ask the questions that are going to split up this pile in the best possible way. That's not going to change. So in our first step here, like the best question to ask is like, hey, is it red, right? And this is how we would probably clean our rooms as well, right? We'd say, okay, I'll take the red pile, move it out of the way. At that point, we've already, for free, we've got, well, not for free, but after the very first question, we get our neatly sorted red pile. And half our books are already sorted. And now we have to ask one more question to sort the remaining pile, right? Okay, so let's analyze this through the same lens that we were looking at the other example a minute ago. The number of questions that it took to sort the red samples was 1, and the probability in this case was 1/2. The number of questions it took to sort the blue, though, was 2, and the probability was 1/4, and the same is true for the green. So what we actually find, amusingly enough, is that this actually works out yet again. So the very same math is going to apply even in this case. We're going to be able to figure out how many questions does it take to sort that class. Well, it's still log base 2 of 1 over the probability of belonging to that class. So that math still is going to work out even when we look at these sort of more imbalanced data sets. Does that answer your question, Isaiah?
Yeah.
Cool. All right. So that, believe it or not, is more or less the hard part. We're now, hopefully you have an intuition for like why log base 2 of 1 over the probability of something actually shows up. That's at the core of the expression for entropy, actually. If you look at the entropy expression, you'll see there's like, oh, log base 2 of like 1 over the probability, or equivalently negative log base 2 of the probability. Laws of logarithms, right? If you do log of 1 over x, that's the same thing as negative log of x. Anyway, doesn't matter if you don't know that. Bottom line is the expression for entropy hopefully will make a little bit more sense now. And now what we're going to ask is, okay, so I know how to figure out the number of questions it's going to take to sort a class if you tell me what the what the probability of that class is. So that's fair enough. But I'm not interested in a specific class. I'm interested in knowing, on average, how many questions does it take? How much work do I have to put in to sort an average point in this data set? If I were to close my eyes and reach in and find a point, or pick rather a class, how much work would I put in without knowing what that class was beforehand, right? So in other words, on average, what is the expectation value of the number of questions that I would have to ask? What is the weighted average, in other words, number of questions, weighted by class, right? In this case, right, we have more red samples, so the odds that we're gonna end up picking a red sample are actually like higher than the odds that we'll pick a blue sample, for example. So we'll want to weight the one question possibility higher, right? So like 50% of the time you end up with like just asking one question, but then 50% of the time you have to ask two, right? So for blue and for green, you have to ask two questions. So what is the average number of questions that we have to ask? Well, in this case, it's like 50% times 1 plus 25% times 2 plus 25% times 2, and on average, it's going to be 1.5 questions. Okay, so the average number of questions that you have to ask in order to sort this like pile of books or these samples is 1.5 in this case. And that is the actual entropy of that data set. So that's what that number says. The entropy is, if you imagine a new sample with a totally unknown color, totally unknown class, how many questions should you expect to have to ask in order to sort it? That's the entropy. And just to put in kind of in equations what we just said with words, that's what we're doing down here. It's a weighted average of the number of questions you'd expect to ask for each class. So you look at like the probability, for example, that the sample is red, times the number of questions that you have to ask if that sample is red in order to sort it. So again, probability that the sample here is red is 1/2. The number of questions you have to ask if it's red is just 1, plus the probability that it's blue times the number of questions you'd have to ask if it turned out to be blue, plus the probability that it's green, and so on. So this is essentially, it's a weighted average of the number of questions that you would ask in each case, weighted by the odds that that's the number of questions that you'll have to ask because it belongs to a particular class. So ultimately, this is where the expression for entropy comes from, and that's where this summation stuff pops up again. So it is the sum of, that's just what X is the different classes, by the way. So for all the different classes, what is the probability that a sample will belong to that class, and then what is the log of 1 over that probability? That's the entropy. If the math doesn't make sense, totally cool. You can also just remember it's about how many questions on average do you expect it to take to sort a jumble of points. The more disordered that jumble of points is, the more it's a mix of all kinds of different classes and it's a total mess, the higher the entropy is going to be. So lower entropy means more pure buckets, and a higher entropy means, hey, you still have a lot of work to do to keep sorting this until your buckets are pure. Any questions about that? No questions? Okay, I mean, that's pretty much a wrap. I mean, this is the entropy, that's the definition. I think, yeah, like, I would recommend trying this out, like, come up with a jumble of classes and calculate the entropy, and convince yourself that, you know, you can actually reason through it. Maybe if you're working on a classification problem, see if you can, you know, evaluate using the entropy, even calculate it by hand if you want. And it should make some sense. Yeah, I mean, entropy is, it's a really deep topic and something I recommend looking into if you're curious about it. Kind of expected more questions. I think this session usually takes more, but oh yeah, Austin, go ahead.
So it would then apply for each column within your data or each dimension, right? You would need to run the same calculation for each class. Is that correct? If you have multi-dimensional data?
If you have multi-dimensional data. So what's
like say our points weren't just blue and green and red, say they were also triangles and squares and circles, then you need to run that for the shape as well, right?
Oh, yeah. So yeah, good point. Essentially what we're using here is just the labels, right? So the idea is like the blue and green and orange and all that stuff, that represents the training label. And so that we're always going to assume is one-dimensional because we're assuming a classification problem with a single target variable.
Okay.
But you're right that, like, you know, if there were multiple things that you were interested in predicting, there would be a different entropy value associated with each thing, each variable that you're trying to predict. You know, so if you're interested in predicting not only like a person's income, but also like, I don't know, their weight, then you would have, you know, one entropy value for the weight prediction and another one for the income one.
Okay. Okay, so it's really for the target variable, seeing on average how many binary splits you'd need to be able to get to the given value, any given value.
Exactly.
Okay.
Yeah, and how many, to be even more like pedantic about it, it's like, yeah, how many splits on average would you expect to, yeah.
Awesome.
There is, by the way, a related value called basically the Genie Index, sorry, the Genie coefficient, and basically this is it moves like entropy. So when entropy goes up, the Genie value goes up, but it's actually somewhat simpler to calculate, and either entropy or Genie value can be used to train decision trees in scikit-learn. So that's one really cool thing. If you use decision trees in scikit-learn, you can actually like train them using entropy. And in that case, literally what those trees are doing is by trial and error, they'll take your data set and they'll be like, like what if I split it in this way? And then they look at the piles and they go, okay, yeah, these piles are definitely cleaner, than this pile up here. The entropy is lower. So that's a great split. I'm going to keep that split. And then they keep going, like, okay, let me see if I can sort like the resulting piles. Okay, you know, oh, those piles look really clean. Great, I'll keep that split. So this is, for those of you who've attended the office hour where we talk about decision trees for regression problems and how you can train them for regression problems, it's the same idea. It's just that you're going to use something like entropy to build the tree out. That's the variable that you'll end up using.
Awesome.
Yeah, any other questions?
So would the metric of entropy exist before you actually create a model, or is it like after you have made the model? Does it evaluate the model?
Oh boy, that's a great question. Yeah, actually, this is where we start getting almost philosophical. Entropy is a property of a data set. You're right. It doesn't depend, at no point do we need to invoke a model. So we can just look at this pile of points. Forget about everything that happens after. Forget about whether or not we're looking at a machine learning model. Any data set that has a target variable that's categorical, like any classification type data set, it already has an entropy, right? If your data set's this disordered jumble, if you've got like roughly even amounts of all the different classes, the entropy is going to be really high. And you can actually interpret a machine learning model. Actually, like I was saying at the very beginning, you can interpret the job of a machine learning model as being something that takes a high entropy data set and turns it into a low entropy data set, or a number of low entropy data sets. And so that's really where the idea comes from. At every intermediate step along the way in that process, your data set will have a well-defined entropy, right? Any data set has an entropy. Yeah.
Okay. Great.
Cool. And any other questions about any of this stuff from anyone? It's open season, man. Okay. Oh, yeah.
I mean,
Isaiah.
how is entropy used in evaluation in terms of if we extend beyond, like we already have entropy, how is it useful beyond knowing that this data set's clean or unclean or whatever?
Yeah, it's a really good question. So the interesting thing about entropy, or the relevant thing about entropy is higher entropy means like your data set's a mess, and lower entropy means your data set's really clean. One of the challenges, as you've seen here, is that entropy is a lot less interpretable than certain metrics. So it's like harder to go to a customer and say like you would never want to go to a customer and say, hey, I made you an algorithm that has like a test set entropy of like 0.7 or something. I don't know. But because those numbers seem meaningless, they happen to be really good for tree-based models, for training tree-based models, precisely because, as you can see here, like the entropy is built with a tree-based structure in mind. So the symmetries of the loss function, the symmetries of entropy as a concept, map onto the symmetry of the problem you're trying to solve. So very useful for applications like that. Really intuitive almost for your computer to understand, because entropy directly maps onto what it's doing here. But ultimately, entropy is not the greatest metric to use just on its own. Like, you can definitely show relative entropy values for different models. You can show entropy improvements and so on. But when it comes to actually reporting your results, I would use precision, I would use recall, I might use accuracy or F1 score, depending on the nature of the problem, what's relevant. But entropy is like, I guess it's a useful metric to understand deeply because of its implications for your training process and how different models work. But it isn't the kind of thing that you'll usually be reporting on its own. Usually people will want like something more intuitive to work from. Does that make sense?
Yeah, thanks.
Cool. All right. Oh yeah.
Sorry. So just, you said like reducing the entropy of the model or of the data is kind of a part of the machine learning model that you're building. How do you take a secondary measurement of the entropy? Like, do you measure it before and after the model? What's that second measurement?
Yeah, great question. So if you imagine what what your model is doing is, well, let's take a COVID example. You start from this data set that's a mix of like, I don't know, 50-50 people who have COVID and people who don't. So the entropy of that is going to be quite high because it's just a jumbled mess. And hopefully what your model is going to produce is two piles, right? So you have all the people that your model said had COVID and all the people your model said don't have COVID. And you can see, because you actually have during training, you have the true labels. So you can look after your model's finished with your data set, look at those true labels and go, is it true that this pile is basically all pure COVID and this pile is pure non-COVID? And the entropy is what tells you that. So yeah, that would be the mechanics of it.
Okay.
And in fact, that's what you get when you use scikit-learn's entropy function, which you can use. So essentially, that's what it'll be doing.
Okay. Awesome.
Cool. Well, I think I'll leave things there. I think finished a little bit early, but feel free to message me if you have follow-up questions on any of this stuff. If you understand entropy, by the way, like at this level, if this presentation made sense, at least the intuition behind it, you are way ahead of an awful lot of people. Like the vast majority of people do not get entropy. They don't even get precision and recall. Like it's really valuable, and I would argue it's one of the best differentiators you can come up with to just be really damn good at model evaluation metrics, because it puts you in touch with the business side of the equation, being really good at thinking about like how your mathematical problem relates to a business problem. And that's one axis that, again, I'm biased, but I think it's an axis that like many people fail to look at and companies really care deeply about. So anyway, with that, I'll leave things there. Again, feel free to reach out to me on Slack, and have a great rest of the day, everybody.
Thank you.